Hey, hi, my name is Daniel. Thank you for coming out here. So this talk is inspired by Orwell's 1984. We're going to see how we can use some ideas from the book to apply to our daily programming, hopefully in a useful way. If you're asking yourself why 1984, then it's just because I really like this book and this analogy is quite fun, and I had like great time actually delving into it and deriving it. So hopefully you'll enjoy it as well. So first, a quick recap of yes. Oh, sorry. Better now? Yes. Oh, switch. Now better? Oh, whoa. Better now? Okay. So quick show of hands. How many people here actually read the book? So, oh, quite a few. Okay. So a very quick recap of the book. Just the main points I'll be slightly using and abusing throughout this talk. So the book describes a dystopian future. At the head of the government is the party, which controls everything. And at the top of the party is one of the most iconic images of the book, Big Brother, which is always watching and sees everything. And one of the methods of control used by Big Brother and the party is the language, newspeak, which is designed in such a way that so as to limit people's ability to express various ideas, forbidden ideas or anything else. Some examples of newspeak are thought crime is what happens when you think of something which is forbidden. Non-person is what happens to you if you actually did this. And in reality, you become erased from all existence and history, and you're just completely gone. And the last point here is an example of a newspeak term, double plus and good, which just illustrates how you can sort of minimize the language by reusing small parts, smaller parts of the language itself. Now, the focus of the talk are the three party slogans. So, war is peace, freedom is slavery, and ignorance is strength. So, those slogans might seem quite negative to some of you, I guess. But as we'll see, those can inspire actually useful techniques that we can apply to our daily programming. And so, this you can view it as an outline for this talk. So, each slogan will be mapped or inspire some technique that we're going to explore, and we'll just go over them one by one and see the connection. A quick disclaimer, so this is just an analogy, so don't take it too seriously, obviously. Whatever I might say or not say, you're not thought criminals, whatever you're doing in your daily jobs, even if it's Java. But whatever you're doing, so be careful, since Big Brother is actually watching all the time, so be advised. So the examples in this talk are going to be code-driven, and I'll start with something pretty basic. Hopefully, it will be familiar to all of you. Just recast it in the light of the book. And the second part should be slightly more advanced. Hopefully, some of you will see something unfamiliar and new in there. And the last part might be somewhat too advanced for some of you, but hopefully, it's like a glimpse into new ideas that you can apply and learn more about in the future. So, what is peace? Well, I claim that this is peace. Now, this code is quite horrible. You don't actually have to read it. It's just here to intimidate you. So I'll just throw it away. So the reason why I call this code peace is because it embraces a number of enemies. Specifically, we have side effects and immutability, which you're not the crowd that I should be convincing that they are indeed quite evil and should be avoided. We have nullability, which obfuscate the flow of the code, making the logic of the code harder to track. We have exceptions, which make the control flow of the program harder to follow as well. And we have multiplicity, is what happens when we try to apply a loop around some computation and derive multiple results from a single thing. And again, it somehow manages to obfuscate the flow of the code, making it harder to read and reason about. And all of these things are instances of effects. So effects are things that typically make it harder for us to understand what we're actually doing, and those are the enemies that we're going to open war against. And so the code on the previous slide was embracing these enemies, and we would like to somehow battle them and hopefully vanquish them out of our code forever. So to actually achieve this goal, we'll need to have some sort of a battlefield where the war will commence. And for this purpose, I'll use a running example, a toy example. And inspired by one of the recurring themes in the book is that 2 plus 2 can equals 5, and something that the party can make you believe. We can actually model it as programmers into reality. So we'll start with a small language for arithmetic expressions. So we have 3 cases here. So a single data type expression has 3 cases: addition, multiplication, and values. And we can write an evil function in the obvious way for it. So evil goes case by case. So we have 2 plus 2 equals 5, obviously, and the other cases are the obvious implementation that you might derive yourselves. So, and we can use it, and it returns the appropriate result, as you might expect this. So 2 plus 2 actually equals 5. So this achieves the goal of the party as required. And so with the battlefield ready, we can actually go on to our first enemy. So the first enemy is side effects immutability. And again, I won't be convincing you that side effects immutability are indeed quite bad. So much so that ideally the language that we're using should make it difficult up to impossible to express. And so I'm going to, and Scala and other languages are not that good at doing this. So I'm just going to pretend that side effects immutability are just not available in the language at all. And so I'm just going to pretend the enemy away and just move on to the next enemy. Okay, nullability. So what does it mean for something to be nullable? It means that a value that we expected to be present might be missing. So like the ampersands in the book, which happen to be missing all the time. And so since we're dealing with numbers, we're going to make a number disappear. So here's a variation of the evil function from before, which makes the number 7 disappear. So as you can see now, the value 7 becomes null. And so the price that we're paying for this, for the ability to make something disappear, is the fact that everything now is wrapped in null checks. So this code is somewhat harder to follow. And then, sorry. So apart from actually being repetitive and hard to follow, this code is less safe than the previous code, since the compiler knows nothing about the nulls, and so if we fail to actually make a check here, we might fail at runtime with an exception. And this is obviously not a good thing. But nonetheless, despite the shortcomings, this code does actually what it's supposed to do. So the question is, how can we make it somehow better? How can we fight the enemy and make it less painful to work with? And so in order to actually achieve this, we need to somehow understand the essence of the enemy we're fighting. For this purpose, we'll try to be as precise as possible. And one of the most precise ways of doing something in programming is to define a special type that defines the problem we're trying to solve. And so in this case, we'll have a dedicated type called nullable of A, which represents a value of type A that can be missing potentially. And so this type has 2 possible states. One is when the value is present, so we just wrap around a value of type A and pass it on. Then the other case is when the value is missing, and so this is just a constant, which we just return as the missing case. And so we can now rewrite our evil function from before using the nullable value, and this will look as follows. So instead of returning a plain number, we're now returning a nullable event. And the solution is actually quite similar to what we had before, but it's much safer. So now the compiler actually knows that we have to return a nullable event, and so it will force us to do the pattern matchings here explicitly. So we can't avoid doing the pattern matches without a compilation error. So this code is still quite ugly, but at least it's safer. So that is an advantage. And the question is, how can we get rid of this repetitive pattern of pattern matching? So if you think about it just a little bit, you can actually see what's exactly the pattern here, which we're trying to capture, and we can factor it out into a higher order function. So we'll do just that. So we're going to define the chain nullable function. So what chain nullable does? So given a function that produces our next nullable value, we're going to try to apply it to our current value that we're currently processing. So in case the value is present, we're doing the pattern match once and for all. So in case the value is present, we're going to apply the function. In case it's missing, we're just going to propagate the error downwards for the next step of the computation. And so this abstracts away the pattern of pattern matching that we saw on the previous slide. And we can use it like so. So as you can see now, it's much cleaner and just as safe as before. So no more explicit pattern matching, no repetition of the same pattern over and over again. but it's still slightly more obfuscated than the ideal solution. So we still have some levels of nesting here, and to one scale, if you have more nullable values, we'll have more nesting, but just the code becomes less and less readable. And so the question is, how can we get rid of this problem? So if you have some experience with functional programming, this pattern is actually quite recognizable, and it's one of the most well-known functional abstractions, and specifically this is the well-known monad abstraction. And so for our purposes, the essence of monad is the flat map function. And so we can view it as a generalization of the chainable function from before, just working on any type constructor f that takes a single type parameter. And so you can read it as follows. So suppose we have some value wrapped in f. We have a function that produces our next value given an a, and we can somehow join them together into a single computation that produces an f of b. And so a chainable is just a special case of this more general function flat map. And having noticed the fact that we're dealing with monads, we can recall that Scala has special syntactic support for monads, specifically the for comprehension syntax, and we can use this to simplify our code. And so the final version of Vivo looks like this. So we're using for comprehensions, or monad comprehensions, and which is just syntactic sugar for the flat map calls that I defined before. And so our actual logic is now completely flat and as apparent as it can be, so we're just evaluating two parts and joining them together. And in the background, the for comprehension syntax takes care of propagating errors and doing whatever needs to be done for this to actually succeed. So we are living on the happy path just by telling what to do when the values are present. And flat map, or the for syntax, takes care of just propagating the errors down the line as appropriate. So having completely isolated our enemy behind a type, behind a specific dedicated type and the monad abstraction, our code is now in real peace. So by peace, I mean it's not obfuscated at all this time. And so having dealt with this enemy appropriately, we can move on to our next enemy, and this will be quite a bit shorter since we have some experience. So the next enemy is exceptions. Armed with the knowledge of nullability, we can just skip ahead to the point where we just define the essence of this problem as a type. So we're going to define a new type for exceptions. So a computation of that yields a value of type A, but that can potentially fail with some error, is going to be represented by an exception of error and A. And once again, we have two cases. One when the value is present, so we have OK of A, and the other one when we have an error. And so this time it's not a constant. We do actually have an error value, which can be like a string or anything else. And so we can now represent exceptions using this type alone. And seeing how useful was the monad abstraction on the previous enemy, we're going to define flat map straight away. And so flat map does the obvious thing. We're just pattern matching on our current value, taking a function that produces a new exceptional value, and if the value is present, we just apply the function. But if not, we're just propagating the error down the line and continue our computation. And so here's an example of using the new exceptional values. So we have a new version of the evil function. So in this case, we can possibly yield an exception in form of a string, and so we can see that multiplication now is forbidden. But notice how little the rest of the code changed. So apart from producing errors, the rest of the code is exactly the same syntax as before. The for syntax takes care of doing all the hard work for us. It just propagates errors as appropriate, and we're still on the happy path. So our enemy is still isolated behind a dedicated type and an abstraction, and still we can remain in peace, having opened a war against exceptions. And this brings us to our last enemy on the list. Oh, sorry. We can actually evaluate this, and this works as you might expect it. And this brings us to our last enemy, so multiplicity. And so the question is, what is multiplicity? So it means that a single computation can yield multiple results. So this is the case where the hero of the book experiences that 2 plus 2 can yield multiple values. And so we can model it again with a dedicated type that captures the essence of the problem for us. And so a single computation that yields multiple values is just a list of values. So we can just reuse the standard list type for this purpose. And list defines the obvious implementation of flat map for, so we don't have to do it ourselves. And so we can just skip ahead to an example of using lists. So in this case, what changed is the fact that we're now 2 plus 2 equals both 3 and 5 together. But again, the core logic of the function remains exactly the same. We have the same for syntax as before, and it takes care of all the magic for us in the background. So in this case, when we evaluate the function, the flat map calls or the for comprehension syntax takes care of cross-referencing all versions of computation and providing a list of results for us. So again, we managed to achieve a level of peace by opening a war against this specific enemy. So this concludes our war on effects, and we can sum up. So we should try and recognize enemies in our code for what they are, effects, such as nullability or exceptions. We need to try and capture their essence in the most precise possible way, preferably some type or some other precise abstraction. Along with the type, we should try and minimize the damage from the enemy by wrapping it in some dedicated abstraction, like the mod abstraction that we used before, but there are many others. And once you've done all that, having opened an all-out war against effects, your code can be truly in peace, like in the examples before. And so, indeed, war is peace. And this includes this part. Okay, so to our next slogan, freedom is slavery. What is freedom, again? One day, your boss comes in and tells you that our great library from before is now ready for production, so we can ship it to our clients. And we do just that, and so our clients starting to use our library, and they're just using it, as they might be expected to do. And so they're just going quite crazy with it, making more and more difficult expressions, and like completely nuts. And one day, you're seeing this expression. Anyone spot the problem with this specific expression? Probably not, but let's focus on the numbers. More specifically on this. And so obviously a subversive message against Big Brother, so this cannot be. And your boss comes in, back again, and he sees it, and he's not happy about it, not happy at all. And this cannot pass without the obvious punishment for such treason, obviously. And so the question is, what went wrong? So what have we done? What was the mistake that led us down this sad path in our lives? Well, in this case, it's actually quite obvious what was the problem. So if we look back at our definition of our expressions, we can see that the constructors for our data type are completely exposed. We've given our users full freedom to do whatever they want with this data type. And for the freedom that we gave them, we are now slaves to the consequences of this freedom. In this case, enslavement means that we can't verify the correctness of code produced by our library. And so we cannot be certain, so the value from before, the wrong value that we stumble upon can actually exist. And so the problem is excessive freedom, so the solution will be to somehow take the freedom away. In this case, it's actually quite simple. We just slightly modify our data type to accommodate this lack of freedom. And so this is Scala-specific syntax, but the general idea applies anywhere by, so you can use it in other languages as well, but by marking the type constructors and by the data constructors with a sealed abstract, make it impossible to create new instances of expressions outside our own source code. And so users can no longer create expressions on their own. And so in order to actually be able to use this library, we need to somehow provide them an interface to work with. And so for this purpose, we're going to introduce another bit of code, which will be smart constructors. So they're smart in the sense that they're going to do the construction work, but also verify the correctness of the input. And remembering that war is still peace, we're going to use the nullable type from before to mark when a value is invalid. So a missing value would be the result of removing invalid values. And we can implement this function quite straightforwardly. So we pattern match on our inputs, and if it's the wrong value, we're just returning missing, but otherwise we're creating a new instance of the addition type. We can do the same thing for the other constructors, so we can have cases for multiplication for plain values. And in this case, we don't actually have any special validation, so we just leave it at that. And using this code, these smart constructors is actually quite simple, given that we have the for syntax from before. So as you can see, creating a valid value still works as expected, but trying to create a wrong value is failing. And so by limiting the freedom of the user code, we managed to make it impossible to create illegal values in our programs. So we're no longer slaves to the choices of our users, which is a good thing, obviously. More generally, though, picking the right amount of freedom to give our users, and so that they can actually use the library productively, can be quite tricky and requires some experience or something else. And so let's look at another example just to illustrate the point some more. And so again, our boss comes in and tells you that what we did here was censorship. And obviously this is great. We should do like more, way more. And so, but the censorship that we implemented up to this point was quite primitive. So let's have like more interesting requirements for censorship. So this is the goal for this part. So we're going to process expressions. The process can either fail within message or succeed, or as sometimes censorship does, it can silently rewrite the input, just because. And so since we're already used to using types to model our problems, we'll just have a special type to do just that. So type censor exactly captures the requirements. So we are processing expressions. We're returning exceptional values. So this can either fail with a message, which is a string, or succeed, which is the expression. And since the expression here can be any expression whatsoever, this can also amount to silently rewriting the input that we got. So this seems to answer all of our requirements for this problem. And we can try and implement a rule using this new type. And so here's the new rule. It does a few things at once. So first of all, it silently rewrites 4 to 5. 7 is still a non-person. We also added some limitations on what you can do with addition and multiplication. But still, the core of our code looks exactly the same as before, the same 4 syntax. So war is still peace, and still we have the same happy path to live on. And we can try and apply this rule to specific expressions. So here's an example. So we're applying this to a valid value, and we get an OK value in return. But notice how 4 was written into 5. Here's another example where we did something wrong. So 7 is a non-person, so we get an error message. And this is what we seem to require. So we do have an error message. Sorry, we do have a problem here. Since 7 is indeed a non-person, but also multiplying by 3 and adding 9 is also illegal. But we only have a single error message. And so the question is, what gives? Well, obviously, we couldn't have any other outcome since our type specifies explicitly that we can have only a single string as an error message. So obviously, we could not expect it to have multiple values and multiple strings as error messages. And since the problem is with the type, we can try and fix it by tweaking the type. So let's somehow accommodate this new requirement for this purpose. And so instead of returning a single string, I'm going to return a list of strings. So we'll be able to somehow accumulate the errors as we go along and produce a list of error messages instead of a single message. And so we have to now rewrite our censor type. So it's almost exactly the same, except that we're now wrapping everything in lists. And the for syntax, as we're now used to, should somehow magically cross-reference all possible combinations, just do the right thing for us. That's the magic of our comprehensions. So we can try and run this rule again, and the result is sadly quite disappointing. So we have a list of errors, but it's still a single error. And so this is not what we wanted at all. So this doesn't answer our new requirement. And your boss, again, comes in saying that you're suppressing important ideological content. And this saddens him greatly because he worked very hard for these messages. They're like very sophisticated. Of course, it can be set for only so long, and eventually this anger sets in, and of course you'll be punished again. And so it's again time to ponder our mistakes. So now that we're unpersons, we have all the time in the world. So what went wrong again? What was the problem with our solution? Well, we can take step back again to look again at our type. So everything started with a type, so probably the mistake is still there. So our type is using the exceptional value from the exceptional type from before. As you recall, the interface of working with exceptional values is the monad abstraction that we've shown previously. So this is it. And if we actually examine the signature of flatmap, we can deduce the problem just from reading the signature. So let's try and just read it. So think of f as some action that produces a value. So given an action that produces a value of type A, we can inspect the resulting value and choose our next action based on this value. And so and the whole process produces a single action that produces a value of type B. But the question is, what happens when the first action doesn't produce an actual value, doesn't have an A value? This is exactly what happens in the exceptional case that we in the exception type. And so we don't have an A value, so we don't have anything to pass inside our function, so we'll never choose the next action. So essentially, flatmap short circuits the computation for us without us even intending it to do so. It just can't do anything else. And we can look at it from another point of view, is that flatmap gives us too much freedom. Specifically, it gives us the freedom to choose one action based on the results of the other action. So we're inspecting the results of the previous action to choose our next action. So this is quite a lot of freedom. But if we were looking at a specific use case that we had before, and this is just the same code from before desugared back into flatmaps, we see that we're actually not using this freedom at all, since rule of B doesn't depend on the result of rule of A. So we're given some freedom, and we just abused it. And the price we're paying is, again, slavery in some form. In this case, we cannot somehow extract useful output from our computation. So again, the problem is excessive freedom. And the solution will be to somehow limit this freedom of our interface. So monad won't do for us. Monad is just too free for our purposes. And the question is, how can we find something else to replace it that limits the freedom of the interface and provides the right constraints? Luckily, there are many other abstractions in the world of functional programming, and we can just look at them and try to find the right one. So here's one very simple abstraction called Functor. It abstracts over things that can be mapped over. So given an f of A and a function from A to B, we can produce an f of B. This is obviously much weaker than monad, since you cannot implement flatmap using map alone. But sadly, this is too weak for our purposes, since you cannot do much with it at all, and you cannot solve the problem that we have at hand only with Functor and its map function. So we can try and look for another abstraction, something more powerful. And the next one on the abstraction ladder is applicative. So applicative extends the functionality of Functor with two more functions, and the core one is the map2 function here, and it can be read as follows. So given some value, some action produces a value of type A, and some action produces a value of type B, we can combine both of them into a single action by use of a regular function. And this is stronger than Functor, since you can implement map using map2 and unit alone. And it's also weaker than monad, since you cannot implement flatmap using map2 and unit. But what's crucial for our point here is the fact that these two actions that we are combining are completely independent. So the evaluation of f of b doesn't depend on the evaluation of f of a. So this constraint or lack of freedom is exactly what will let us accumulate errors as we want to achieve. So let's see how this comes about. So we'll start out again with a brand new type for our purpose, just to avoid the pitfalls from before. So the censorship type, again, has two cases. One where the value is present, so it's a passing case, and one where we have a list of errors, so a list of strings, since we want to accumulate errors inside a single list. And now instead of defining the flatmap function like we did before, we're going to limit our freedom and define only the applicative interface. And so here's the definition. It's quite straightforward. Just go case by case. So given FA and FB, two values of censorship, we're just seeing the various cases, just act accordingly. So given a pass of A, pass of B, we just apply the function to it and pass on the computation. If one of them is failing, we have nothing to do but just pass along the errors that we have, so it's a failing case. And the last case, which is the crucial one for our purposes, is when both of them are failing. And so we have access to errors on both sides, of the computation, and we can combine them into a single error value and produce a single accumulated error value. This is exactly error accumulation as we desired to achieve previously. And we can put this to work by using, again, defining the new censor type that takes an expression and produces censorship of expression, and not the exceptional type from before. And we can rewrite our rule from the previous slides. It's quite similar to what we had before, since we just used the fail and pass instead of the other constructors. But the crucial part here is the addition case. Now, since we're no longer using flatmap, we do not have access to the for comparison syntax, so it's slightly uglier. But what's critical for our purposes here is the rule of B and rule of B are evaluated independently. Each one of them will be evaluated regardless of the result of the other, and only then we'll combine the results into a single value. And so this is exactly error accumulation as we wanted, and we can run this code on the expressions from before. So the first case is just as before, but the second one now contains all three error messages that we wanted to collect. So we managed to achieve accumulation. So by limiting the freedom of the code, we've managed to actually produce some useful output from our computation that we couldn't before. And so to conclude, freedom on one level is slavery on another. So when given freedom, when given excessive freedom at some point, we're bound to be enslaved to its consequences later on. this can be the risk of producing incorrect results like in the first example, or the inability to extract some useful information from the computation like in the second example. And more generally, limiting the freedom of code helps us reason about it, since the less it can do, the more we can say about what it actually does during computation. So this is a huge benefit that we can use for our advantage. Of course, one can be tempted to just take away all freedom from code, just completely. And that's a bad way to actually do anything, since then the code will be completely unusable. So like the example with the functor abstraction, which didn't allow us to actually achieve our goal that we tried to solve. And so we have to choose the exactly right amount of freedom and give exactly that, not more, not less, since if we give more, we're again at risk of being enslaved. And so once you, and having decided on the right amount of freedom, one can actually start to quantify freedom by using more concrete abstractions, like more concrete mathematical abstractions like applicative, functor, mod, and many others that are available to you. So when you start using them, choosing the right amount of freedom becomes just taking the right step on the abstraction ladder. And so knowing your abstractions well is something that will help you achieve this goal of choosing the right amount of freedom to have in your code. And so this concludes this part. So last slogan for this talk. Ignorance is strength. So before we begin this part, I'm just going to announce more enemies of the people. All of these things are, I'll pretend they just don't exist in Scala at all. And this is not much of a loss, since typically we just want to avoid them anyways. So, okay. And I'll just pretend them away. And so let's start again with ignorance. So can anyone guess what this function does? No? Okay. So I tricked you, obviously. The name of function doesn't guarantee anything, and it shouldn't guarantee anything, but the problem runs somewhat deeper. Since this function operates on concrete ints, it can use any information it has about integers to produce the result. And so we can't know what it does, since it can do anything that's possible with integers. So we have like excessive knowledge in this function, which makes it impossible to reason about what it actually does. And so the question now is, what happens if we erase this knowledge, if we make this function more ignorant of its specific context? So let's write this function. Now we have a type parameter, a generic type A. Can you guess now what this function does?
It returns A.
Oh, right. So why is this so? Now, since A is a type parameter, it's completely abstract. We know nothing about it. We're completely ignorant of the specific context that it was given to us, in which it was given to us. So we can't do anything with it. We can't operate on it. And we can produce them out of nowhere. Since A is completely abstract, we can't just know how to produce an instance of it. And since the only A in scope that we have is the input value, we have to return it. Okay? And so this property that helps us reason about functions which are parametric is called parametricity. And it's called parametricity, and which in our case translates to the fact that the more our inputs are constrained, so the more generic our inputs, the less we know about them, the more our outputs are constrained, the less we can do with those inputs. And so from ignorance, we manage to gain some strength. We can reason about what this function does. Of course, not every function is completely determined by its type signature. Obviously, some functions are slightly more complicated than the identity function, but the general point still stands. You can reason about parametric functions in a way that is more powerful than you can reason about concrete functions. Not only that, we can actually help catch bugs with parametricity. So here's another example. This is the swap function, and in the first case, obviously, I have a bug. I wanted to swap the two elements, but I didn't. And this is a runtime bug, which will just catch me somewhere in production, and I don't know. And what would happen if we go and erase the specific knowledge of the integer types here and produce a completely parametric type, function? So it takes two type parameters, A and B. And what happens is that we can now, just by reading the signature of this function, we can guess what it does exactly. So if given a tuple of A of B, it produces B of A. Obviously, it has to swap the two elements. What's more important than the fact that we can read this function signature, the compiler can do this as well. And so this code is now compilation error. So the compiler managed to catch bugs for us just by making the function more ignorant of its specific context. So again, ignorance becomes some form of strength. Now, these two examples are quite simplistic, although they do illustrate the point. Real code tends to be ever so slightly more complicated than these two examples. And let's try to construct a more involved example just to illustrate this point. And so, as sometimes happens in bigger organizations, while we were working on our expression library, someone else was doing the exact same work, and they came up with this. So expressions of the second kind, quite similar to ours, but they somehow generalized the addition multiplication into a single constructor, which takes the operation as an argument. And this is quite similar to what we had before, but still slightly different. And we've already implemented very important business logic with our first expression type, and so we would like to somehow reuse it with this definition. Sorry, this definition. We don't want to actually duplicate the logic once more. And so this is actually quite straightforward to avoid duplication. We just need to somehow translate between expressions of the first kind into expressions of the second kind. And we'll do this just by pattern matching on the expressions and so given a binary operation of plus, we convert it into an addition and then recursively convert its subparts into expressions of the first kind. And so this works as you might expect it to. You can apply it to a simple expression, converted expression of the second kind into expression of the first kind. And now to be able to evaluate expressions of the second kind, we can just compose the two functions, the eval function and the translation function. So we take an expression, convert it, and then evaluate it. And we yield the expected results. So the evaluation of this expression is what we might expect it to be. And we avoided duplication between the two data types. So translation helps us avoid duplication. It's a good thing, obviously. But now, again, our boss, nagging as it was, tells us that our clients are going crazy with our library. They're creating huge trees of expressions. And our solution is actually quite inefficient, since we're making two passes over our trees, expression trees, to first evaluate them, first translate them, and then up and down, and then evaluate them again up and down. So this is quite inefficient, and Big Brother cares about performance quite a bit, obviously. And so the question is, how can we make it somewhat more efficient, like take a single pass over the tree up and down and somehow evaluate it and translate it in a single round. So if we look at our eval function, we see we have a problem. Since the eval function combines evaluation, which is the plus multiplication or just the values, with tree traversal. So the recursive functions here are traversing the tree for us. And so since this is part of the definition of a function, we cannot fuse it with another function, since the traversal of the expression tree happens directly in this function. And if we could somehow extract the traversal from the evaluation, we might be able to somehow fuse this function with the translation function. Now, this pattern of recursion is actually quite repetitive. If you work long enough with expressions, you'll see this pattern come up more and more. And maybe from studying another example, we'll see it will be easier to refactor the pattern out of this definition. And so here's another example of a function. It does something quite similar, but instead of evaluating expressions, it produces strings. So it's a pretty printer for our expression language. And we can see the repetitive pattern here, so it's the recursion here. And we can summarize this pattern as follows. So given some type A, which can be either strings or integers, what we're doing is somehow convert the subparts of the expressions into values of type A. And then we combine the two A values, be it strings or ints, we combine them into a single A value and pass it on to the next step of computation. Now we could somehow abstract away this pattern using a higher order function like we did with Chainable. But if we think about it more closely, this pattern is dictated from another level of definitions. And specifically, the original expression type is a recursive data type, and in the sense that it references itself in its own definition. So the references to expression here are recursive references. And as you can see, the recursive references occur exactly at the spots where we're doing recursion in the functions. So if we could somehow remove the recursive nature of this expression, make it oblivious of its own recursive nature, we might be able to somehow separate away the recursive part of our functions from the evaluation part. And since we're used to working with types, we'll define yet again another type. So an expression step designates a single step of evaluation of an expression that yields a value of type A. And we have three cases, mimicking the cases of the original expression type. Notice how the recursive references from before are now replaced with the generic type parameter here with A's. So we've removed the recursive part of the expression completely. And so add step designates the following. Suppose someone already computed two A values for us. Add step combines them into a single value ready for processing as an addition expression. Multiplication does the same thing, and value step wasn't recursive to begin with, so it just remained the same. And using this new data type, we can now re-implement our eval function. So the eval function now will work on expression steps of type int. And so we can try and read the main branch here. So the addition step branch here says the following. So suppose someone already computed A and B for us and converted them to numbers somehow. I don't know how, but somehow they managed to do it. And so the question is, what will we do with the two values? So, and the answer will be combine them using addition. Same goes for multiplication. So as you can see, this is just the evaluation logic from before without anything about recursion. So we're not recursing on the data type, we're just doing one single step of evaluation and stopping at that. Someone else will have to be responsible for recursion for us. I can do the same treatment for the translation function from before. So we can now make a single step of translation between expressions of the second kind into expressions of the first kind. And so the branch, first branch here can be read as follows. So given a single binary operation of plus, so we peel off the plus, convert it into a single addition step, and then we take the two sub-expressions and leave them unchanged, ready for processing in the next step. So again, this is the same logic from before, but we stripped away the knowledge about recursion. So this definition is completely ignorant of the fact that this is supposed to be some kind of recursive process. Now with this in hand, we can try and fuse the two functions. So here's the signature that we can try and implement. So given a translation function, it takes expressions of the second kind into expression steps, and given an evaluation function that reduces expression steps of integers into integers, provided we have expression of the second kind, produce a single number. Now this is quite specific to our problem domain. We're encoding the specific parts of our problem directly in the signature. And can we make it more ignorant of its context, since we know that ignorance is strength? So we can try and make it more generic and just pull away the type arguments. So I've switched the type arguments from before into type parameters. And so now it's a more generic function that given a way to generate expression steps of A and a way to reduce expression steps of B into B, provided an A value, produce a B value. This is much more generic than before, less info about our specific problem, but still quite specific to our domain, since we're using expression steps. And the question is, can we use something even more generic, like any container type that just wraps values that we can work with? So we can try and do this signature. So given some type constructor, it takes a single argument, f, so some context for our computations, provided a function that unfolds a's into f of a's and a function that reduces f of b's into b's, given an a, produce a b. And this is quite ignorant. We know nothing about our original problem. And sadly, this is too ignorant for our purposes, since how will we be able to actually work with f values? We know nothing about them. Like, they're just completely abstract the type constructors. We have no interface to actually operate on them. And so how can we actually do anything with them? And the answer is we can't do anything with them at all. We'll need some sort of interface to access these values and manipulate them. And for this purpose, we'll have to reintroduce back some knowledge about our problem. And luckily, we do have some minimalistic interface that allows us to work with the values of type like f here. And this is the functor abstraction from before that we saw previously when freedom was slavery. It still is. And so functor allows us to map over f of a, given a function from a to b, produce an f of b. And so this is the most minimalistic interface you can possibly have for working with type constructors. And so we can use this to bring back some knowledge about our problem back into our type signature, and this will yield the final type signature for our purpose, and it can be read as follows. So given a type constructor f that implements a functor, it has a functor interface, given a function that unwraps a's into f of a's and a function that reduces f of b's into b's, provided an a, produce a b. Now, this is as ignorant as we can get, and supposedly it's supposed to give us more strength, and it does, since working at such abstract level constrains the solution so much that we can actually derive the solution by just sort of following the types. And it's exactly what we'll do. We just follow the types and derive the solution. And so we start with an a value. We have a single a value, and we have a single consumers for values of type a. This is the from a function. We can just apply from a to a, producing an f of a value. Now, we don't actually have any consumers for f of a, so we're kind of stuck. At this point, we must recall that f implements a functor. And so if we had a function from a to b, we might be able to convert f of a into f of b. And it doesn't look like it looks like it, but we actually do have a function from a to b in scope. Specifically, if we partially apply fuse to the first two arguments, we have a function from a to b. So fuse applied to the first arguments is the right type. And we can now apply this function to our f value. So we can map it over f of a. And this produces an f of b. And now we do have a consumer for f of b. So this is a 2b function. So we apply 2b over fb, and this produces a b value, and this is exactly the result that we wanted to achieve, and so we return this result. And this might actually sound kind of ridiculous, but this, this solution derived like mechanically just by following the types is actually the solution to our problem. It actually does the right thing for us. And so just before we can actually apply it and use it on actual code, we have to implement the functor interface for expression steps. And this is quite obvious how to do it. We just take the function, apply it anywhere where we can, and ignore it where we can't. And so with this in hand, we can actually use the diffusion function. So we taking a single expression of the second kind, we fuse the translation function with the evaluation function, apply it to a single expression, and produce the right result. And the fact that we could just work at such abstract level and just achieve our goal still blows my mind, even after actually doing this myself. And if you don't actually believe me that this does the right thing, here's a trace of execution of evaluating this example. I won't go step by step, just you can do it at home if you really want to. But you can see that we're going down the tree, and we're translating as we go down, and we're evaluating as we go up. So every subtree is being translated and then evaluated on the way up. And this is exactly the behavior that we wanted. We managed to become slightly more efficient than before. So by making ourselves completely ignorant of the specific problem, by making the code as generic as possible, we managed to achieve the ability to deduce code almost automatically. So the compiler just helps us derive the code for us. So we managed to gain some strength. And so we need to strive to remove as much knowledge from specific knowledge from our code as possible, since not knowing the exact context in which the code works upon constrains greatly the output of this code. And we can use this constraint or this ignorance about our inputs to our advantage, be it the ability to determine some aspect of the implementation of the function, or allowing the compiler help us write code. And so, indeed, ignorance is strength, as I wanted to prove. And this concludes this part. Actually, I really like this quote. It just kind of fits the context exactly. To recap, we've seen that each of these slogans maps into some useful programming idea. I hope you were convinced of this. War and effects brings peace to our code. Freedom on one level is slavery on another. And ignorance can be leveraged to help us reason about code or even derive it. So I find this as a message, as a way to preach functional programming to your coworkers. This is like a great way. Just print it out, put it on your office wall, and just work along. So some further reading if you're interested. So the full code for this presentation, the presentation itself is available on GitHub. A more detailed introduction to monads can be found in Wadler's paper here, Monads for Functional Programming. Great resource for more abstractions is Typiclopedia. It's in Haskell, but still very useful for learning about new abstractions. The part about freedom is slavery was inspired by Runar Bjarnason talk, which is who's attending the conference as well. Constraint slavery at liberty is constrained. Ignorance is strength. The parametricity, which I hand waved about, is formalized and popularized by Wadler's article "Theorems for Free." And the fuse function is just one instance of a very wide topic called recursion schemes. And there are talks in this conference about recursion schemes. And this idea was popularized by this article by Meyer and others. And a more accessible introduction, less academic, it can be found in this series of blog posts, which just explains it in a more down-to-earth way. So this concludes my bit. Okay, so we're done. Thank you very much.